Hello, this is a video for section 17.7. I'm going to call this part 2 of the video, and I'm going to start from slide 107. So at the tail end of the previous video, we were solving this problem, and then I got to the end of it, and I made a slight mistake, and so I trimmed the video, and I had to use some software, free software online, to trim the video, and so you will see their banner on the bottom. I am sorry about that, but I wanted to trim and then do the rest of it in this video. So here we are. We finished off with this example, so I'm going to review this a little bit. We're calculating the molar solubility of AgCl in a solution which has a common ion. So that's 0.200 molar sodium chloride. And then we're going to compare it with the molar solubility that we get off AgCl in pure water. And they already have the value for you, 1.33 times 10 to the negative 5. So we set up an ice table for the AgCl solid, and then this is the external source of the chloride ion. So they're adding 0.200 molar sodium chloride. And so in the solution, you will have an extra amount of chloride, which is 0.2 molar. And so we're going to add that to the ice table. And then we do the usual calculation and solve for X. So X is 8.85 times 10 to the negative 10 molar. This is where I made the mistake. This is correct here. So on the next slide, I did a bunch of calculations. And you should see all of this in the previous video. So here I made a mistake. This was written as 10 to the negative 5. It is actually 10 to the negative 10. So I carried it over incorrectly. So at the beginning of the video, you would see an incorrect value, and at the end, I would have corrected it to 10 to the negative 10 molar. So I'm showing you again how with the common ion effect, the value of X is 8.85 times 10 to the negative 10. This is the molar solubility of AgCl when you have a common ion. Next, I'm going to do a comparison here. What's the molar solubility of AgCl in just water? Let's say you did not have the common ion. And so you will do the calculations like this, simple like we've seen before. And the X value that you get is 1.33 times 10 to the negative 5 molar. So what happens to the molar solubility when you add a common ion? So I'll show the comparisons on the comparison on the next slide, so it's less confusing. So what is the molar solubility of AgCl? Using a black ink pen, AgCl in 0.200 molar sodium chloride. Okay. So on the previous page, let me make sure that I'm writing my numbers correctly this time. Molar. And then molar solubility of AgCl in pure water. So there's no common ion effect in pure water. And we saw more of the AgCl going into solution, and that's why we have a larger number. See that? So AgCl is more soluble. I'm not writing straight. Is more soluble in pure water, but it's less soluble in sodium chloride. So let's look at the equation one last time. In accordance with Le Chatelier's principle, okay, you're trying to see how much of this goes into solution. Because when you write the ice table, you say excess of this, initially 0, 0, minus x, plus x, plus x, okay? So how much of AgCl goes into solution is given by x. So in pure water, it's this number. When you have the common ion, okay? When you have a common ion, what happens? It shifts the equilibrium to the other side. So then the value of x naturally decreases, okay? So that's what we are proving here. The solubility of AgCl in this is 8.85 times 10 to the negative 10 molar, which is about 5 orders of magnitude smaller, okay? So the solubility is decreased. So you're not letting the AgCl solid go into solution. It suppresses the dissociation. So when you add a common ion effect, the value of x becomes smaller because it's pushing the equilibrium to the left-hand side. I hope you understand that. And so I wanted to clarify this point, and therefore an extra slide and more time in part 2 of the video. Okay, so we saw what the common ion does to the equilibrium when you have a sparingly soluble ionic compound. Now, there are certain cases, and you have seen this example in lab, in your Le Chatelier's lab. Okay, and you used magnesium hydroxide. Magnesium hydroxide solid goes into solution as Mg2 plus and 2OH minus AQ. So it's producing OH minus. And what you did there was you add an acid. You add an acid. And so when you add an acid, okay, H3O plus, let's say HCl, could be H3O plus and Cl minus. The H3O plus will react with OH minus. You will produce 2 molecules of water. So what are you doing indirectly is you're applying a stress and you're decreasing the concentration of your product. Okay? Decreasing the concentration of your product. So what happens to the equilibrium if this concentration decreases? OH minus concentration decreases. So then QC will be, let's see, products over reactants. So if you decrease that, QC is less than KC. Okay, decrease the product, QC is less than KC. So then the equilibrium will shift to the, think about it, the equilibrium will shift to the product side. Remember, you added phenolphthalein and things like that. If you go back to the lab, you will recollect this. Equilibrium will shift to the product side. And what will happen here? We are concerned about solubility. what happens to the solubility? More of the solid will go into solution. And you did test this. You will see the solid, the white solid on the bottom, decrease in amount. And then you also did, you tested the reaction in an ice bath and in a hot water bath. Okay, and you saw it shifting from being cloudy to clear, or going from having a lot of solid on the bottom to becoming clear. Okay, so here, how is pH affecting the solubility? That's what we're looking at here, not how heat affects the solubility, but how does pH affect the solubility? So naturally, you have free hydroxide ions in solution, with magnesium hydroxide going into, with magnesium hydroxide dissociating. But then if you have a way to remove the hydroxide ion, and because this is basic, you can add an acid, and the acid will react with the OH minus, and it will bring it into solution. And therefore, indirectly, you're decreasing the concentration of OH minus. Okay, one of the product concentration is decreased. So then QC is less than KC, and the equilibrium will shift to the product side. More of the solid will go into solution. And then here, so increases the solubility of the compound. Okay, increases the solubility of the compound because more of the solid is going into solution. So X, if you were to do the calculation for X, the value of X increases. Okay, so if more of the solid goes into solution, that means your value of X is increasing. So you have a case where you have a basic anion produced in solution. Okay, a basic anion is produced in solution. And it says here, it's a little tricky the way it's written. It is also true for anions that are weak bases. Okay, a basic anion here, I'm going to be very specific, something like the OH minus ion. Next, we are going to look at anions that are weak bases. Okay, so these are, for example, the conjugate bases of weak acids. Got that? So one, you have an OH minus ion in the structure of the compound, and it goes into solution to give OH minus ions. Secondly, if you have a weak acid and the conjugate base that it produces is a weak base. So we'll look at examples on the next page. So these are the two kinds that will be affected by pH. The solubility of these compounds will be affected by pH. So let's look at some examples. One, this is the first case where you have OH minus ion in the formula. Okay, the first case that we saw on the previous slide. So here, Hg, OH twice, goes into solution. Okay, so now we have to read the question. We just started working through the structural characteristics of the problem, of the compound. The question is, which one will be more soluble in acidic solution, okay, rather than a neutral or basic solution? So again, you have the free OH minus ions. If you add H3O plus, concentration of OH minus decreases. And the molar solubility of HgOH2. Okay, this is mercury 2 hydroxide. The molar solubility of HgOH2 increases. Okay. Hence, it will be more soluble in water. Okay, that answers the first question. It's similar to magnesium hydroxide. I don't see anything different. So anything that has an OH minus ion in the structure, when you add an acidic solution, then more of the solid will go into solution. More of this will go into solution. It shifts to the product side. Okay. Of course, you have to write AQ and all that bit. Next, okay, I'm going to look at CDF2 first, and then I'll look at CUBR. Okay. I'm going to use the bottom part, so I have room for the second one. Cadmium, we don't use it very often. Okay, a solid. It's dissociating. So the question is, will this be more soluble in an acidic solution? So this belongs to the second category. Okay, belongs to the second category. I'm going to pull up the slide, the previous slide. Anions that are weak bases. And what are these? These are conjugate bases of weak acids. So F minus is an example. The acetate C2H3O2 minus is an example. Okay, there are lots of weak acids. Their conjugate bases are weak bases. Okay. F minus, I'm going to take F minus, and this is all in water, right? This is all in water. So this is a weak base. And where is its origin? Comes from HF, which is a weak acid. Remember our analysis of acetic salts, basic salts, and neutral salts. Okay, so this is a weak base coming from a weak acid. And look what happens. F minus plus water gives you HF plus OH minus. So F minus itself, there's no hydroxide in the formula, but what does F minus do? This is a weak base that reacts with water. And what does it do? Look at that. It produces the hydroxide ions. Okay, it produces the hydroxide ions. So because it produces the OH minus ions, if you add acid, more F minus will convert to HF. And then what happens? The concentration of F minus will decrease. See that? And so I'm going to put a star there. And if concentration of F minus decreases, which way will the equilibrium shift? Equilibrium will shift to the product side. Okay, equilibrium will shift to the product side. And then what happens? CdF2 is more soluble in water. All right, so you're adding H3O plus, and CdF2 becomes more soluble. So when you increase the pH, CdF2 is more soluble in acidic conditions. Got that? So this is the anion of a weak base. Therefore, I'm sorry, an anion of a weak acid, okay? Therefore is a weak base of considerable strength, and it's quite reactive with water. Same reasoning, quite reactive with water, and it'll produce HF and free OH minus ions. So anytime you make OH minus ions, the H3O plus can come and neutralize the OH minus ions, and therefore this concentration decreases. You'll have more of the F minus going to form the OH minus ions. So what happens to the previous equilibrium? This is decreasing because it's wanting to make that with water, and therefore the equilibrium shifts to the product side. When equilibrium shifts to the product side, the value of X, the molar solubility, will decrease, which means this guy is more soluble in water, okay, roundabout way. So hence this conclusion. All right, now let's look at the one in the middle, Cu and Br. Now you have to start thinking about the role of Br minus. Where is this guy coming from? What is his origin? Let me put a, so it looks like you can concentrate on that problem alone without being distracted by the other writing part or the written part. This is a, this comes from HBr. And what about HBr? It's a very strong acid, okay? So Br minus, the conjugate base, of a very strong acid. So what do we know about this guy? This guy is very stable and therefore no reaction with water. I hope you remember that. Br minus is a very stable ion. Okay, very stable ion. And therefore, he is not reactive with water. He's stable as he is. Now, so he's not producing any OH minus ions, and he's not acidic. Br minus is not acidic. and therefore CuBr will show no reaction when you add an acidic solution or a basic solution. So this will not show any changes. I'm going to leave it at that. Will not show any changes in an acidic solution. Okay, will not show any changes in an acidic solution. Got that? Okay. So just two simple things. Is there an OH in the structure? If it is, then yes, H3O plus will affect it. Now, do you have an anion that is a weak base? How do you know it's an anion from a weak base? This anion will come from a weak acid. Okay, that's all. And then you explain it this way. But if the anion is from a strong acid, then he's not going to react any with water to produce OH minus ions. So CuBr will not be more soluble in acidic solution. Okay, so that explains that part. It's not too difficult. You just have to know how to identify your anions in solution. Now, with that, we complete this. We've already done this. It just was a slide that was sitting underneath the other sheet. So I'm going to wrap this one up, 17.7, and then I'm going to shoot another video, and that will be looking at Ka values and Ka values of weak acids and things like that. Okay. So I hope this clarified a lot of things for you. I hope so. And I'll see y'all in another video.